All right, in 11.2, when we're talking about techniques for evaluating limits, this is just that more algebraic approach. So we're going to use the dividing out technique, where the dividing out technique is really where we're going to factor and to see if we can eliminate any of our factors to help us simplify to be able to plug in our limit. Rationalizing will mean that you have to multiply by a conjugate. And then potentially having to use our graphs or our tables to help us figure out the limit. And then we're going to get to the one-sided limits. We're not going to use the difference quotients. So we're not getting into that in this section. We're just going to end with the one-sided limits. So the first thing is your dividing out technique. And so remember, when we're finding limits, whenever they have the limit is approaching some constant, your first step should be that you are trying to substitute that constant into your polynomial to see if you get a real number. And if you get a real number, then that's what your limit is. So if we were to substitute in our -3, we would get -3 squared plus -3 minus 6 over -3 plus 3. And if you simplify that down, you get 0 over 0. So when you get 0 over 0, your limit will exist. You just have to do a few things to figure it out. So if you ever get 0 over 0, don't say the limit doesn't exist. Like that 2 zeros gives you kind of that clue that it does exist. It's just you're going to have to simplify it or get it into a different form first. And so that's where that dividing out technique comes in. So when you look at your table, let's say maybe then you look at your table. If this was our table, you would look at your table and say, okay, as we're coming in from this way, we're getting closer to -5. And if we're coming in from this way, we're getting closer to -5. So there's a pretty good chance that our limit will be -5. Right? And so the dividing out technique pretty much tells you that what we're going to do is we're going to factor it to try to eliminate some of our factors in there so that way we can actually substitute in our constant. So here's that same equation that we just had. When you're showing your work for these problems, this limit notation right here has to be included in every step. So if you tend to be someone who tries to take a few shortcuts in your work and you don't have the limit in every step, and then all of a sudden a -3 just ends up in your equation for your x coordinates, your reader's not going to necessarily know where that -3 came from, right? So you have to include that, otherwise it's... All right, so what we're going to do is show our work, and we're going to say the limit as x approaches -3, and we're going to factor. So our numerator would factor into x plus 3 and x minus 2, and our denominator just stays with that x plus 3. So what we find out then is the reason that our function doesn't have a value at -3 is because we have a hole in our graph, since we have the same factor in the numerator and denominator. So we can eliminate the hole, and we find then that the limit as x approaches -3, we just have x minus, it should be minus 2 left. So what this means is that this graph right here will look exactly the same as this graph right here, except for the one in the top will have a hole and the one in the bottom doesn't. So sometimes when the book asks you for what's another function that will look the same as the one you started with, it's really that idea of once you take out the hole, then you have that similar function. So once you're to this step, now you can substitute that -3 in for x, and you end up with -5, which from the table is what it seemed like the limit should be. Okay, so -5 would be our answer. All right, so then the next technique is to rationalize. So if you see a square root as part of your limit and you can't actually plug the value in because you get 0 over 0, or you end up with undefined, because if we plug in the 0 here for this example, you would get the square root of 0 plus 1 minus 1 over 0. which would mean that you get 0 over 0. And remember, if you get 0 over 0, your limit exists. You just have to reformat your equation. So what we're going to do is we're going to rationalize our numerator. So we're going to say the limit as x approaches 0 of the square root of x plus 1 minus 1 over x. Right, so that's, and then we're going to multiply by its conjugate. So the square root of x plus 1 over the square root of x plus 1 plus 1. So the goal in multiplying by the conjugate means we're going to eliminate that radical in the numerator this time. So when we FOIL this out, we would have the limit as x approaches 0. Our numerator, when we have root x plus 1 times root x plus 1, we just get x plus 1. We get the plus and the minus, so that middle term becomes 0. And then negative 1 and 1, we get minus 1 over x times the square root of x plus 1 plus 1. And I really wouldn't simplify that denominator because that's usually where you're the canceling out when the numerator and denominator will help you. So if we rewrite this, we have the limit as x approaches 0 of x over x times the square root of x plus 1 plus 1. And now look to simplify. And since we didn't distribute that x in the denominator, what we find is that this x in the numerator and that x in the denominator will simplify. And we're left with the limit as x approaches 0 of 1 over the square root of x plus 1 plus 1. And now we're to the point where we actually can then plug in the 0. So 0 plus 1 plus 1, which gives you 1/2 for your limit. All right, so moving on, sometimes the dividing out and the rationalizing won't work, and so you'll go to your calculator. And so if we have something like an example 4 where we have the limit as x approaches 0 of 1 over x to the x, 1 over x. If we were to plug in the 0 and you get 1 over 0, 1 plus 0 to the 1 over 0, right? This up here is an issue because it's undefined. So you can't just, again, say undefined. We don't have an algebraic approach for this yet at this level. So what we'll do is we'll go to the table in our calculator. So what I want you to do is in your y equals, I want you to put in your 1 plus x raised to the 1 over x, and then go to your table as x is approaching 0. So then once you have your table, again, at 0 there's an error. And when you're looking at the left and the right, it's not the same number. So if it was the same number on both sides, then you would probably say, yep, that's my limit. But the fact is that those are different numbers. So what we're going to do is we're just going to average these two numbers together because we're so close, and then we'll use that as the approximate limit. So to find the limit, we'll take our 2.7196. We'll add it to the 2.7169 and then divide it by 2, which gets us 2.71825. And that's what we would say is our approximate limit for that one. So again, when those table values aren't exactly the same on either side, you can just average those two together to get that approximate limit. All right, so next one, approximating the limit graphically. So this time I want you to graph e to the x minus 1 over x, and just from looking at the graph, look to see what does it look like the y value is when your x is approaching 0. All right, so you get a graph that looks like this, but what you find is that when you actually look at the value where x is approaching 0, and if you were to calculate that value at 0, your calculator is not going to give you a number. So if you go to trace instead, and you trace a little bit to the left, and if you go a little bit to the left, you see that your y value is 0.9. And if you go a little bit to the right, you see that your y value is about 1.1. You can probably make a pretty good estimate that the limit at 0 will be, what do you think? Probably 1, right? So for a lot of the graphs, it can become pretty clear as to what the limit is just by looking at the graph. But you could always then go into your table if you want to just make sure as well. Because obviously if you have your calculator to graph it, then you have your calculator to look at the table. And then the last thing are the one-sided limits. So with one-sided limits, it means we're really just looking as it's approaching either from the left or from the right. And the way that you know it's one-sided is that you have these little markers after your constant. So if you have the negative sign, it means that you're looking as the graph comes from the negative direction. And the negative direction would be the left side of your graph. So it's approaching from the left. If you have the little plus after your constant, it means that we're coming from the positive direction. And the positive direction is from the right side. So it won't necessarily tell you that you're looking for your left or your right hand limit. It might just say find the limit. So you might have a question that says, find the limit as x approaches 2, and it'll have this, and then it'll follow up the function. And so it might be, or of the function, and then maybe they'll give you a graph. And so you would have to understand that they're saying we're only looking for that y value as it's approaching from the right, not necessarily from both sides. So let's look at this equation here. We have the absolute value of 2x over x, which was similar to one we did in 11.1. So if we were graphing that, that's under the line. If we were graphing the absolute value of 2x over x, and we're looking for the left and right hand limits as x approaches 0. So if we were to make our table for this, and we're looking for when our x is 0, let's look at left-hand values. So if we plugged in a -3 for x, again, we would have the absolute value of -6 over -3, which would give you -2. And if we plugged in -2 in for x, we would still get a -2 for y. And if we plugged in -1 in for x, we would get -2 for y. 0 is undefined. So here, this part of our graph, as we have the negative values, would look like that, just that horizontal line at -2. And then as we go with the positives, what we find is that our y coordinates are all +2, but still undefined at 0. So we'd still have an open circle, but then we would have a positive graph that way. So if we were identifying it, this right here would be where our limit, we would say the limit, as x is approaching 0 from the left, and we would have that little negative sign there, of the absolute value of 2x over x. And that limit would be -2. Because from the left, the y values are approaching -2. If we were looking at this part of the graph right here, though, we would say the limit as x approaches 0 from the right of our absolute value of 2x over x, that would be +2, because we're approaching a different value. So then what we know then is that the limit as x approaches 0 does not exist, right? And the limit at 0 doesn't exist because your left and right hand limits are approaching different values. So if left and right are approaching different values, then the general limit doesn't exist. But you can still identify a left hand limit and a right hand limit. So this last thing here, the existence of a limit, again, is the idea that your left and right hand limits both have to exist and have to be equal in order for the limit to exist. So let's look at this last example. And we need to find the limits as x approaches 1. So let's first find the limit as x approaches 1 from the left of our function. And from the left means from the negative direction or from the values that are less than 1. So this top equation would be when x is approaching 1 from the left is what equation we would use for that. And so in this case then, we would plug the 1 in for the x. We would have 4 minus 1, and we would get 3. And then if we wanted to find the limit, the right-hand limit, so x is approaching 1 from the right, then that means that we have to use the values when x is greater than 1, right? This is when x is approaching 1 from the right, because those are the values that are more. So for that one, we would do 4 times 1 minus 1 squared, which would also give us 3. So in this case, our left and right-hand limits are equal, even though our function isn't defined at 1 because it doesn't ever equal 1, so we must have a hole at both of those points. But the fact is that your left and right are coming into that same hole in your graph, so you could actually determine then that the limit as x approaches 1 is also going to be 3. So even without having to graph this piecewise function, you could potentially determine the limit just by finding out if that left and right hand limit are the same. So it can save you a little bit of time and not having to graph piecewise functions by using left and right hand limits to figure out what the actual limit is of that piecewise function.